Welcome to this comprehensive tutorial on activation functions beyond ReLU. We're going to explore a variety of modern activation functions that have been developed to address the limitations of the traditional ReLU function. This tutorial covers everything from the baseline ReLU to advanced functions like GELU, SiLU, and Mish. We'll see how each function works, when to use them, and compare their performance. By the end, you'll have a complete understanding of which activation function to choose for your specific neural network tasks. Let's begin with an introduction to activation functions. These are crucial components in neural networks that introduce nonlinearity, enabling networks to learn complex patterns. While ReLU has been the go-to activation function due to its simplicity and effectiveness, it has limitations that newer activation functions address. We need different activation functions because of issues like the dying ReLU problem, where neurons can become permanently inactive, the need for zero-centered outputs for better gradient flow, smoothness for improved optimization, self-normalization to maintain stable distributions, and task-specific performance where different functions excel in different domains. First, let's import all the necessary libraries we'll need for this tutorial. We're importing Pytorch and its neural network modules, NumPy for numerical operations, Matplotlib and Seaborn for visualizations, and setting up our environment with consistent random seeds for reproducibility. Great, we have Pytorch version 2.5.1 installed and ready to go. Now I'm creating a helper function that will allow us to visualize each activation function along with its derivative. This visualization tool will help us understand how each function behaves across different input ranges and how their gradients flow, which is crucial for understanding backpropagation. Let's start with ReLU, the baseline activation function. ReLU stands for rectified linear unit, and its formula is simply the maximum of 0 and x. It's simple and computationally efficient, creates sparse activation with many zeros, doesn't saturate for positive inputs, but suffers from the dying ReLU problem. ReLU is best used for general-purpose deep networks, when computational efficiency is critical, in CNNs for computer vision, and when you want sparse representations. Core code. Here we're visualizing the ReLU function and its derivative. Notice how ReLU outputs 0 for all negative inputs and passes positive inputs unchanged. The derivative is either 1 for positive inputs or 0 for negative inputs, which can cause the dying neuron problem when neurons get stuck outputting 0. Looking at the plots, we can see the characteristic hockey stick shape of ReLU. The function shows a sharp transition at 0, and the derivative plot reveals the discontinuity at 0. The example input shows how negative values become 0 while positive values pass through unchanged. The main advantage is its speed and simplicity, but the dying ReLU problem and lack of zero-centered outputs can be limitations. Moving on to Leaky ReLU, which solves the dying ReLU problem. The formula allows a small negative gradient when input is less than 0, typically with alpha equal to 0.01. This prevents neurons from dying completely by allowing small negative gradients to flow through. Core code. Now I'm visualizing Leaky ReLU with different negative slopes. We'll compare how different alpha values affect the function's behavior. A smaller alpha like 0.01 creates a very slight negative slope, while larger values like 0.3 create more pronounced negative slopes. The plots show how Leaky ReLU maintains a small gradient for negative inputs, preventing the dying neuron problem. We can see 3 different negative slopes, from the subtle 0.01 to the more pronounced 0.3. The derivative shows continuity except at 0, and the example demonstrates how negative values are scaled down rather than zeroed out. This simple modification of ReLU prevents dying neurons while maintaining computational efficiency. PReLU, or Parametric ReLU, takes this concept further by making the negative slope learnable. Instead of fixing alpha, the network learns the optimal negative slope during training. This gives more flexibility than Leaky ReLU and can adapt to different layers' needs. Core code. I'm demonstrating PReLU with a learnable parameter. We'll see how the negative slope parameter adapts during training. This shows the key advantage of PReLU. It can learn different slopes for different layers or even different channels in convolutional networks. The visualization shows PReLU with its learned alpha parameter of 0.25. The right plot demonstrates how this parameter evolves during training, adapting to minimize the loss. This adaptability is PReLU's main advantage, as it can learn optimal negative slopes for your specific data. However, it adds more parameters to learn, which could lead to overfitting with small datasets. ELU, or exponential linear units, introduces smooth and differentiable behavior everywhere. For negative inputs, it uses an exponential function that asymptotically approaches negative alpha. This creates negative outputs that help push mean activations closer to zero, which can improve learning dynamics. Core code. Let's visualize ELU with different alpha values. The exponential behavior for negative inputs creates a smooth curve that saturates at negative alpha. We'll compare how different alpha values affect the saturation level and the overall shape of the function. The plots show ELU's smooth exponential curve for negative inputs, saturating at different negative alpha values. Unlike ReLU variants, ELU is smooth and differentiable everywhere, including at zero. The comparison shows how alpha controls the saturation level from negative 0.5 to negative 2. The smooth gradients and negative saturation can help with vanishing gradients and provide noise robustness, though the exponential computation makes it more expensive than ReLU. SELU, or scaled exponential linear units, is a special variant with self-normalizing properties. It uses specific values of lambda approximately 1.0507 and alpha approximately 1.6733 that maintain mean close to zero and variance close to 1 through many layers. Core code. Here I'm demonstrating SELU's self-normalizing property by passing random data through multiple layers. We'll compare how SELU maintains statistics compared to ReLU and ELU. This is crucial for very deep networks where maintaining proper activation statistics becomes challenging. The plots beautifully demonstrate SELU's self-normalizing property. While ReLU and ELU show degrading statistics through layers, SELU maintains mean close to zero and standard deviation close to 1 throughout the network depth. This remarkable property enables training of very deep, fully connected networks without batch normalization. However, it requires specific weight initialization and works best with fully connected layers rather than convolutional layers. CELU, or continuously differentiable ELU, is a mathematically improved version of ELU. While ELU has a gradient discontinuity at zero, CELU ensures the gradient is continuous everywhere, which can lead to better optimization properties. Core code. Let's compare the gradients of ELU and CELU to see the continuity difference. This visualization will show how CELU eliminates the gradient discontinuity at zero that exists in ELU, potentially improving optimization behavior. The gradient comparison clearly shows the key difference between ELU and CELU. The ELU gradient has a visible discontinuity at zero, jumping from the exponential derivative to 1. In contrast, CELU's gradient is perfectly continuous at zero, creating a smooth transition. This mathematical improvement can lead to better optimization, especially with gradient-based methods sensitive to discontinuities. The continuous gradient makes CELU preferable when smooth optimization is crucial. GELU, or Gaussian error linear units, introduces a probabilistic interpretation of activation. It weights inputs by their probability of being positive according to a standard normal distribution. This is the activation function used in transformer models like BART and GPT. Core code. I'm comparing exact GELU with its tan approximation. The exact version uses the cumulative distribution function of the standard normal, while the approximation provides a faster computation. We'll see how close the approximation is to the exact function. The plots show GELU's smooth, non-monotonic shape that differs significantly from ReLU variants. The comparison between exact and approximate versions reveals they're nearly identical, with the approximation error being negligible for most practical purposes. The probabilistic interpretation is evident in how GELU gradually transitions from near zero for negative inputs to near identity for positive inputs. This smooth gating mechanism has proven highly effective in transformer architectures, contributing to their state-of-the-art performance in NLP tasks. SELU, also known as Swish, is a smooth self-gated activation discovered through neural architecture search. The formula is simply x times sigmoid of x, creating a smooth, non-monotonic function that's unbounded above and bounded below. Core code. Let's visualize CELU and compare it with ReLU and GELU. We'll also demonstrate the self-gating mechanism by showing how the input gates itself through the sigmoid function. This helps understand why CELU has become popular in computer vision models. The comparison shows CELU's smooth, non-monotonic shape similar to GELU, but with its own characteristics. The self-gating visualization clearly demonstrates how the sigmoid function acts as a gate, modulating the input. For negative values, the gate is nearly closed, while for positive values, it's nearly open. This creates the smooth transition and slight negative dip that characterizes CELU. Its effectiveness in vision models like EfficientNet has made it a popular choice for modern architectures. Mish is another self-regularized activation function that uses x times tan of soft plus of x. It's similar to Swish, but uses tan instead of sigmoid, creating different characteristics that have shown strong empirical performance, especially in object detection models. Core code. Here I'm comparing Mish with CELU to understand their differences. We'll look at both the functions and their gradients, as well as the absolute difference between them. This comparison helps understand when to choose one over the other. The comparison reveals subtle but important differences between Mish and CELU. While their shapes are similar, Mish has a slightly deeper negative dip and different gradient characteristics. The gradient comparison shows Mish maintains smoother gradients, which may contribute to its strong performance. The absolute difference plot shows they diverge most around -1 to -3. Mish's computational cost is higher due to the soft plus and tan operations, but it has shown excellent results in object detection models like YALOV4. Now let's do a comprehensive comparison of all activation functions side by side. This will help us understand their differences and relationships at a glance. Utility code. I'm creating a grid showing all 8 activation functions with both their outputs and gradients. This comprehensive view allows us to compare shapes, smoothness, and gradient flow characteristics across all the functions we've studied. This comprehensive grid provides an excellent overview of all activation functions. We can see the progression from the simple, piecewise linear ReLU to the smooth, sophisticated functions like GELU and Mish. The gradient plots reveal important differences in how these functions propagate gradients. Notice how ReLU-based functions have sharp transitions while modern smooth functions provide continuous gradient flow. This visualization helps understand why different functions excel in different scenarios. Utility code. Now I'll create a detailed comparison table showing the key properties of each activation function. This includes computation speed, whether they suffer from dying neurons, if they're zero-centered, smoothness, self-normalizing properties, and best use cases. This comparison table provides a quick reference for choosing activation functions. We can see that while ReLU is fastest, it suffers from dying neurons and isn't smooth. Modern functions like GELU, CELU, and Mish solve these issues, but at higher computational cost. SELU stands out with its self-normalizing property, making it ideal for deep, fully connected networks. The table clearly shows there's no universally best activation. The choice depends on your specific requirements and constraints. Let's move to practical examples. We'll train neural networks with different activation functions on a synthetic classification task to see how they perform in practice. Core code. I'm creating a synthetic binary classification dataset and training identical neural networks with different activation functions. This practical comparison will show how theoretical differences translate to real performance. We'll track training loss and final test accuracy for each activation function. The practical results are revealing. The training loss plots show different convergence behaviors, with smooth functions like GELU, CELU, and Mish generally converging faster and more stably. The accuracy comparison shows all modern activation functions outperforming basic ReLU on this task. Mish and GELU achieved the highest accuracies, followed closely by CELU and SELU. These results demonstrate that while ReLU remains a solid baseline, modern activation functions can provide meaningful performance improvements, especially on complex tasks. Now let's create a decision guide to help you choose the right activation function for your specific use case. #utility code. I'm creating a quick reference table that maps common use cases to recommended activation functions. This practical guide will help you make informed decisions based on your specific requirements, whether it's for CNNs, transformers, mobile deployment, or other scenarios. This quick reference table provides practical guidance for choosing activation functions. For general CNNs, start with ReLU for its simplicity and speed. For transformers and NLP, GELU is the standard choice. SELU shines in deep, fully connected networks without batch normalization. For mobile and edge deployment, stick with ReLU or Leaky ReLU for efficiency. Mish excels in object detection, while CELU provides the smoothest gradients. For cutting-edge research, experiment with GELU, Mish, or CELU. Let me provide a comprehensive summary of what we've learned. We've covered 9 important activation functions beyond basic ReLU, each with unique characteristics and use cases. The key takeaways are that no single activation function is best for all tasks. You should start with ReLU, then optimize based on your needs. Modern smooth functions often outperform ReLU. You need to consider computational cost versus accuracy trade-offs, and always experiment with multiple options for your specific task. #utility code. Finally, let's create one last visualization showing all the main activation functions overlaid on a single plot. This gives us a clear picture of how they relate to each other and helps solidify our understanding of their different characteristics. This final overlay plot beautifully summarizes our journey through activation functions. We can see the sharp simplicity of ReLU, the slight negative slope of Leaky ReLU, the exponential curves of ELU and SELU, and the smooth non-monotonic shapes of GELU, CELU, and Mish. Each function represents an evolution in our understanding of how to introduce nonlinearity in neural networks. Tutorial completed. Now you're equipped to choose the right activation function for your neural networks. That's all for this comprehensive tutorial on activation functions beyond ReLU. You now have the knowledge to make informed decisions about which activation function to use in your neural networks. Remember to experiment and validate on your specific tasks, as the best choice often depends on your particular dataset and architecture.